This video is about molecular geometry. In other words, it's about the shapes that the molecules take. Now we're specifically talking here about covalent compounds, things that share electrons, because those are the ones that have individual molecules. Otherwise, the ionic things, the things with positives and negatives, form what's called a lattice. But these guys are individual molecules. So, the prevailing theory with molecular geometry is called VSEPR, V-S-E-P-R. That stands for valence shell electron pair repulsion theory. And the whole idea is all the electron pairs want to get as far away from each other as they possibly can. And non-bonding pairs want to get even farther away because they aren't really constrained between things. So if we want to think about what shape something is, we want to think about it in terms of what's called the center atom. So if you have something like carbon dioxide, then your Lewis dot looks like this, and carbon is the center atom. Now we're going to call the center atom A, and we're going to call atoms directly attached to that X. So this is A, X2. Doesn't matter that they're double bonded, doesn't matter at all. It only matters how many things are directly attached. If I had any lone pairs on the center atom, they would be called E. But since I don't have any lone pairs on the center atom, I have no E. These lone pairs on the oxygens don't count. Now, once you know the pattern, you look on this list. Something that is AX2, something that has two things directly attached to the center atom, is going to be linear, because that's as far away from each other as they could possibly get. 180 degrees. All right, 180 degrees. And it keeps going. Something that has three things directly attached is flat, but in a triangle, and so on and so forth. This is the list. We will make models so you can see what all of these things look like. You do not have to memorize this list. I will always give you this list. Now, what are the consequences of this list? Really, what we care about is intermolecular bonding. That is, what is the bonding between the individual molecules? I mentioned this in the last video. This is where we're going to talk about it. Now, in terms of covalent things, there are essentially three types of intermolecular bonding. The first one is called London dispersion. Now, technically, London dispersion is in between everyone. But what we're going to talk about specifically is the case where London dispersion is all there is. So, two things. If you have London dispersion, one, you have a symmetrical molecule. A symmetrical molecule, i.e., every atom attached to the center atom is the same atom. And two, you have no lone pairs on the center atom. Because if you have lone pairs on the center atom, it changes the shape. It's not a symmetrical shape. Okay? Okay. So, if those two things are true, then the only attraction between molecules is something called an induced dipole. Think about methane, CH4. It's tetrahedral. Okay. These two are in the same plane. This one's coming out at you. This hydrogen is going back away from you. It's tetrahedral. It's symmetrical, but there's no lone pairs on anywhere. So the only attraction between this methane atom and some other methane atom is this idea of a dipole that only exists temporarily. The idea is we have electron cloud around all of these atoms. And electrons are always moving, and they move randomly. So at some point, the idea would be the molecule gets kind of a positive end and a negative end to it. These little d's here mean partial charge. They're Greek d's, they're lowercase deltas. And they mean partial charge. So if one end of the molecule is kind of sort of positive and the other end of the molecule is kind of sort of negative, it means that all the electrons kind of randomly find themselves over here on this negative end of the molecule, leaving this end of the molecule temporarily for a split second devoid of electrons and a kind of sort of positive charge. When that happens, this molecule feels that positive and sort of kind of becomes negative, and this end sort of kind of becomes positive, and it just creates a chain reaction. It's like picture the wave in a sports studio. Why do you do the wave? Because the person next to you does the wave. Why does the person on the other side of you do the wave? Because you just did the wave. That's what an induced dipole is. It's this random, temporary thing that doesn't happen for very long. Hence, an induced dipole. And hence, it's very weak. It's a very, very weak kind of bonding, which is why methane is a gas under normal conditions. Things that have an induced dipole have very, very low boiling point because it doesn't take that much energy to break the bonds, these intermolecular bonds between the molecules. Now, if there's a permanent dipole, for example, H2S, S has 6 electrons, 6 valence. H has 1 valence. If there's 2 of them, it's going to look like this. With 8 to play with, looks like that. These lone pairs on the S make it not symmetrical. It's what they call bent. Okay? So it's not symmetrical. It has these lone pairs. There's what they call a permanent dipole here. Not an induced dipole, but a permanent dipole. A dipole that exists all the time. Okay? A permanent dipole. That makes this kind of bonding dipole-dipole bonding. That is, this end of the molecule up here, because it has these negatives, has that partial negative, but permanently a partial negative. Not a temporary partial negative, a permanent partial negative, giving this guy a partial positive. So some other molecule over here has partial negative here and a partial positive here, and those guys are attracted to each other, right? Positive negatives, they're attracted to each other. It's not an ionic bond because these are only partial charges, but it's an attraction. It's what's called a dipole-dipole interaction, and that is, of course, stronger than the temporary dipole interaction. Now, third kind, stronger still, is called hydrogen bonding. Now, whenever I say hydrogen bonding, suddenly it's, oh, every time there's a hydrogen, it's hydrogen bonding. That's not true. Hydrogen bonding is a very particular case. It's between the hydrogen on one molecule and an N, an F, or an O on the other molecule. Okay? Because these guys are very electronegative. These guys have lone pairs, and they're relatively small. So this H bonding, hydrogen bonding, is really just a special case of dipole-dipole. It's a very strong case of dipole-dipole. So instead of H2S, we have water. Same kind of interaction. The partial negative and the partial positive down here, the partial negative up here. But because it's so very different, because that O is so very electronegative, these are very strong partial charges. This is why water has such a higher boiling point than, say, H2S, which looks very similar to it. But these interactions are so very strong It takes a lot of energy to make water boil. 100 degrees Celsius is a huge amount of energy. So we've got the temporary dipoles of limited dispersion. We've got the permanent dipoles of dipole-dipole interaction. And we've got the H bonding of hydrogen bonding. Remember, hydrogen bonding is just hydrogen and an N, an O, or an F on the other. Special case of dipole-dipole. Then, in fact, if you're thinking about all kinds of bonds in between molecules, then comes ionic, which is why ionic things have higher boiling points than covalent. Those are harder to break. And then from there comes network covalent, like a diamond, which is even harder to break.